One of the most counterintuitive lessons that we learned when building computers that are really good at training deep neural networks at Baidu was the question of precision. Normally when we're building computers, or for example when we're building CPUs, and we're thinking about floating point numbers, we want pretty high precision. There's actually been a trend in high performance computing of moving from fixed point to floating point to double precision floating point and even higher going forward. In the past, the cost of building these units was the hardware units that would perform the floating point operations was pretty cheap, especially compared to the rest of the system. And so it made sense to add more precision. This just would allow for fewer errors in scientific computations. And if it's cheap, why not? It's easier than debugging complicated precision issues. In deep learning, things totally change. And we're instead find that for inference and for training, especially because these are approximate algorithms, we can get away with way less precision than that. And as we're building massively parallel processors that are really focused on reducing the computational cost, the overheads of having really high precision math units, like really big floating point units that are performing computation in high precision, like 64-bit or higher, these are really expensive and the costs add up. So there's a huge benefit in the speed of training and the speed of inference if only we can reduce the precision. But we don't want to go too far. If we go too far, then we end up coming into these complicated convergence issues when training models. We might also lose accuracy when these models are finally trained. And so there's a question of, how much precision do you need? There's a trade-off here between speed and the quality of the output. And so one of the lessons that we learned from a lot of experimental work at Baidu was that the right answer is actually mixed precision, something that we're calling mixed precision. So the idea here is that it's actually a compromise between 16-bit floating point and 32-bit floating point. And let me talk about that in a little bit of detail. But before we get into the specifics, let me talk about some of the benefits. So as opposed to the kind of out-of-the-box computation that you get in accelerators like GPUs, there's some great benefits of moving to a lower precision. So one of the benefits is the size. I mentioned before that neural networks take up a lot of memory, and if we can reduce the amount of memory we need to train them, we can train bigger neural networks, and this can lead to higher accuracy. So, for example, if we started in 32-bit precision, floating point, and we found out that we were able to train storing activations and weights in 16-bit precision, we get a 2x reduction in the memory required. So every single weight matrix, every single activation matrix, the number of bytes required to store them would get cut in half. And this would give us a 2x memory savings. So it's not enormous, but it's a pretty nice bump. It's like having a 32-bit gigabyte or 32 gigabyte memory for the price of a 16 gigabyte memory. That's a great improvement. It also helps with memory throughput. So sometimes neural networks end up just moving around a lot of data, like things like activation functions and batch normalization. They don't do a huge amount of compute, but they move around a lot of data. And because 16-bit numbers are smaller than 32-bit numbers when stored in memory, if you're copying them around, you have to move less data. And so it's effectively like your memory is twice as fast. And this can speed up training, or can also speed up inference. And then the last benefit is actually the biggest benefit. And this is the most counterintuitive benefit. So if you're doing the computation in 16 bits as opposed to 32 bits, you might expect, well, okay, a 16-bit math unit might be a little bit faster, or it might be a little bit lower energy. I might be able to build more of them. And so I might also expect, in addition to the memory savings, I might expect that the accelerator could perform those computations more quickly, or maybe it could perform more of them at the same time in the same amount of area or the same amount of energy. And so, there's a question of, all right, you might expect a 16-bit accelerator to be faster than a 32-bit accelerator, but how much faster? We saw that the memory savings are about 2x, so we might kind of naturally assume that, okay, we're cutting the bits in half, it'll maybe give us about a 2x improvement. This is the counterintuitive point. the improvement is actually a lot higher. And the reason for this is that the area, the number of transistors, also the energy, the amount of data moved inside of the math unit scales better than 2x. So you don't, when you shrink the, especially for a multiplier circuit, when you shrink the number of bits involved in that circuit, you get an improvement that's more like n squared than n. So here, if we look at a concrete accelerator, we look at, for example, a V100 GPU, you can look at the floating point throughput, and you can notice that in single precision, or in 32 bits, the throughput is about tens of teraflops, so it's about 15 teraflops. But if you look at the 16-bit throughput using the tensor cores, it's a lot higher than that. It's actually over 100 teraflops. And so we're getting an improvement in throughput that's closer to maybe 5 or 10 times higher using lower precision or mixed precision. So there's actually a really enormous advantage in the computational throughput that you can get from moving to lower precision. So one of the biggest lessons that we learned looking at the right precision for training deep neural networks at Baidu was that you should use mixed precision. I mentioned that in the beginning, this is a trade-off between speed and accuracy. Higher precision will lead to higher accuracy, and lower precision will lead to a faster accelerator. So what's the right balance? What's the right amount of precision? I think at this point, most people have settled on this idea of using mixed precision for training. In mixed precision, you do most of the math, especially most of the multiplications, in 16-bit floating point. But you might do some of the more infrequent operations, like some of the additions in 32-bit, or some of the accumulation in 32-bit. And this leads to a good balance. You get most of the accuracy benefits of doing everything in 32-bit, and most of the speed benefits of doing everything in 16-bit. We've also noticed that if you try and train a lot of models over a pretty diverse set of applications, like transformer models, like sequence models, like RNNs, like big convolutional models, like giant ResNets, there's very little accuracy loss moving from everything in single precision or in 32-bit floating point to everything in mixed precision. So one of the biggest lessons that we learned is we should train models in mixed precision. There we can take advantage of these really fast accelerators, really large improvements in training speed, and not sacrifice very much accuracy.